Good morning.
Okay, so I guess we are meeting. Usually you send a link around. I didn't get a link.
Oh, perhaps because of the change in our schedule, I didn't get it.
Oh, okay, yeah, I get
Do you
it.
get have you been getting a link every week or every?
Yes, I get a link every week. In fact, that's what I went back to right now. I got that link and clicked on it. I thought maybe that you were on, but usually you send a link right before the meeting, and sometimes I'm always confused about the time. You know, usually there's either 1 or 2 hours, but it's lately been 2 hours difference between our time, Eastern Standard, and your time.
Yeah, well,
Mexico's time.
It's actually scheduled based on international time, so it's scheduled for 1600 UTC.
Yeah, well, that's right. That requires a Google link or Google search.
Yeah. or you have to know what your local difference is.
I have figured that out, but I always forget.
And then they change it every so often, and they change it in different places at different times, and so.
Yeah, that's right. Mexico has decided in some areas not to change their time anymore. Some people like it, some don't.
Yeah, I think in Yusuf's case, he can confirm this, but I think it's 10 o'clock in Mexico City right now.
Yeah, that's what I think too.
Yeah. So that usually it would be 11 o'clock if they had daylight saving time, but I guess Mexico City did not change the time.
Yeah, so that's right. Maybe this new schedule has gone into effect down there, because I always remember it would be 2 hours difference, but then it would revert back to 1 hour's difference. But it doesn't seem to do that now.
Oh, Jesus is back, so we can ask him what time it is.
I think it probably, okay, there he is.
Yeah. Good morning. Good morning.
Buenos dias.
Buenos días.
We were just having a discussion about the time. Apparently, Mexico City is not adjusting the time, right? So you have 10 o'clock.
Yes, now it's 10 o'clock. See, there was a government accord that in Mexico is not going to change more the used time.
Yeah.
Then we have no problem, because we do not need to change anything here.
Yeah. You're so far south that it doesn't really make much difference.
Yeah.
For Canada, it's a big difference from one season, one part of the year to the next. It can be completely dark in the winter, and then still hours of sunlight in the summer. So.
Yeah, in Mexico it used to be more. It used to be more darker in winter, but not too much. And then I think that the change is not the same meaning that in Canada, for example.
Yes. Yeah.
Well, South Carolina is somewhere in between Canada and.
Oh, okay.
There's also talk here about changing the time, but they haven't done it yet, or not changing the time. But I was always used to 1 hour difference, then 2 hours, then back to 1 hour, but now it's just 2 hours difference between here and in Mexico City.
No, okay. Then yeah.
For me, I would just choose international time and say, well, if that, you just set your local schedule according to a different number. It doesn't mean anything, you know.
Well, yeah, I actually, I don't know how that would work, but I certainly think that we should change from inches and feet to meters.
Yeah.
I think that in Mexico we were almost in custom for the change of, but it is to a political position, and then in this way the adjustment to the use time was lost.
Better to be independent, I think.
Yeah.
Okay, well, thank you for sending your updated papers, Dr. Sotrick. I haven't had enough time to actually review your most recent version, but I hope you'll have time today to review the early part of the paper, and then if you can tell us what's new, I think that would be great.
Yeah, I made a list of the most important ideas, and I would start by going through them, and then I'll just use the paper on the screen. But I did write some notes out so I can summarize what I think is the most important ideas there.
I think well, you know, since we've been looking at drafts and we've sort of seen the development, it's probably useful to have to start in a sense from, at least in brief, from the beginning, and then see how the argument develops, as a whole.
Yeah, most important in this newest revision has been my looking more closely at Professor Kaufman's papers, and that in our previous discussion helped me nail down a couple of ideas that I think are important, which I mentioned now. I call it, for example, I call quantum duality this relationship that I always start with, as opposed to the usual duality of vectors and covectors. And I think this idea is important because quantum duality puts together the notions of a symmetric form, which is usually always talked about in terms of quadratic forms of a Clifford algebra or geometric algebra, and the idea of the antisymmetric part, which is just the Grossman algebra. In this algebra of nilpotents, and defining what I mean by the quantum duality, that's what I call it now. I think that's a good term in light of Professor Kaufman's papers. And so the ideas in this new paper, I can see the close relationship, for example, representation of the symmetric group and the ideas that Kaufman has in his papers.
That's good.
I think that's very interesting. And of course, I know that Professor Kaufman was very important regarding this Zbyszko-Ziewicz research seminar of problems in physics.
Okay, and yes, were you going to speak more about category theory today? Did you?
I was working with that, with the idea of start exploring about the category of graphs. I didn't get any to write any slide for this. But I have some ideas that maybe we can discuss, and you can help to me about this, because I have now some difficulties for going ahead in this problem.
Okay.
Then this is the state.
Yeah, that was one point on my list, is the relationship, of course, of this new basis that I can consider extremely interesting of nilpotence in relationship to the graph theory and category theory, of course. And that's what we breached the subject on some of our previous seminars as well.
Yeah, but perhaps, I mean, the strongest connection for me is to clearly define the concept of duality. Category theory has a certain natural concept of duality that arises in a very fundamental way in category theory, but it's expressed differently, I guess, when one considers different categories. So different categories represent the underlying categorical, abstract categorical notion of duality gets reflected in the mathematical structures that are described using category theory. So all of these mathematical structures inherit duality one way or another.
Oh, so how close is that to the usual definition of vector-covector type duality? How close is that in category theory to that idea?
From the abstract level point of view, I'd say it doesn't seem to be very close at all. But if you look more deeply, I guess, at in particular at the category of vector spaces, then you can see that this category of vector spaces, vector duality is definitely related to the abstract notion of duality in category theory. So category theory is a kind of umbrella. It's very abstract and content free. Sometimes just called abstract nonsense for that reason, because it doesn't have sort of how should I say, it doesn't have the natural intuitional representational structure. It's defined in a very abstract manner. It's not until you begin to apply category theory in different subject areas that you sort of see how these subjects that have been studied in separately can be sort of combined under these umbrella notions, and sort of how they are related at the abstract level. So
well, as I mentioned earlier, in my graduate school days, that was after my year came through, they started requiring category theory for graduate students, but I missed that by 1 year. So I'm not so first category theory at all.
I think that we need first to express an algebra in category theory, because the concepts of vector and covector are related with the algebra structure. Then I think that we need to start in this way, and after we can define vector and covector and look how those are related with the duality concept. Then I am not arrived to the definition of algebra in category theory, but I think that we need more concepts for are arriving to this. And then we can explore how in category theory are those concepts. But nevertheless, in category theory, we can speak about one how two categories are related, and then we can get relations that are covariant and relations that are contravariant. And then in this way, we can find how these concepts are related there. Then maybe, I don't know if Professor Garrett is going to start his presentation first, and maybe after of this we can speak about these problems in category theory and how we can relate those with the problem of writing Clifford algebra in graph theory.
Okay, so I think this is all very relevant to just what we've been talking about, namely this idea of what I now call quantum duality. Normal duality, covectors and covectors, really is in Clifford algebra is identifying the quadratic form. That only deals with the symmetric part, and it deals a separate algebra, an independent algebra is separate from an algebra that's co-algebra and so on. Whereas this idea of what I call quantum duality defines duality in terms of the algebra itself. So you're identifying using the symmetric and anti-symmetric part. Perhaps that's more important than the idea of a covector than is the idea of a vector space in its covector space than just separating the symmetric and I think the symmetric and anti-symmetric part should be considered, and that's when you're defining the duality in the same algebras, because any algebra has a symmetric part and an anti-symmetric part, but they don't call that duality. But in quantum mechanics, I think that's exactly what's necessary as a language for quantum mechanics, is to define the concept in the algebra itself that you're working with. In this case, Clifford algebra, or geometric algebra.
But the kind of duality that one deals with in terms of vectors and covectors seems to be of an entirely different type of duality than the relationship between the symmetric part and the anti-symmetric part.
But you need to define two separate algebras, whereas this other concept puts it in one algebra, and of course puts it on the same level as the algebra you start with. But I think it is very closely related, namely the symmetric part of a Clifford algebra is a quadratic form. But even in applications to physics, the line gets blurred when you look at observers. One observer picks out in the Dirac algebra his frame of reference of vectors and bivectors, but in the reference of the another observer moving with a relative velocity, what becomes vectors and bivectors is different. Namely, an electric field is a vector field and a bivector field is a magnetic part. But of course, a moving frame sees an electric field, and then the other observer has a bivector part to it. So this is what's, I think, is why you need to consider the ideas together.
I can see how in physics, for example, electric fields and magnetic fields have a kind of similar kind of duality between, symmetric part of an algebra and an anti-symmetric part of an algebra. That connection seems fairly clear. But in all of that discussion, we didn't say covector even once, right? So So it's like, it doesn't have anything to do, that kind of duality doesn't seem, on the surface at least, to have anything to do with vectors versus covectors.
Well, that's because you're defining a new algebra. When you say a co-algebra, that's not the same thing as the algebra you start with. But somehow I think
You have to be careful with the word co-algebra, because that already has a meaning in category, from the point of view of category theory. If you define an algebra in category theory, then categorical duality provides you immediately with another structure that you call a co-algebra. And it's algebra versus co-algebra, to me, doesn't seem to have anything to do with vector versus covector either. Right? So the use of co in that sense shouldn't be interpreted as implying the same type of duality.
well, that's true. But of course, the idea of a reference frame is extremely fundamental in physics, observer's reference frame. And I think that's where Hesnes' brilliance came out. The fact that he defined the polyalgebra in terms of the even subalgebra of the Dirac algebra. It doesn't matter whether you use matrices or Clifford algebras or whatever. That distinction, every observer has his unit time-like vector of his reference frame, and that's what creates the so-called splitting into the polyalgebra for each observer.
With Professor Osiewicz, we were working around observer algebra. Then the problem was presented like how we can build an algebra between observers that of course are in relative velocity between them. And then those algebra or first the definition of observers have one part covariant and one part contravariant.
Okay, well, that's interesting, of course. And of course,
the tensor product of those parts are the definition of observer, because both the covariant and contravariant part splits all the space, and then with these fundaments we can build an algebra of observers and express the physical laws in terms of one observer in particular, but this takes to us to the presentation of absolute laws of physics that are independent of observer.
That was, of course, one of our objectives. We talked about, I don't know, maybe a couple of months ago, about trying to understand exactly these papers that you and Osiewicz wrote about, all this idea that, he defined these the new things that what was it, the co-group, not co-groups, that a new type of group to describe Lorentz transformations that it's non-associative, and what Bill was talking about as well, these relationships of this, what takes three frames to completely define a Lorentz transformation, or whatever those ideas were. I can't remember.
Yeah, the words that you're looking for is groupoid, I think.
Oh yeah, group.
Yeah. So the notion of a groupoid is something that's easily defined in category theory, of course. And so Dr. Osiewicz sometimes referred to the relativity theory that he was working on as categorical relativity, partly for that reason, I think. But it's Yeah.
Well, that's right. Each language really limits what a person can say. For example, Egyptian mathematicians used unit fractions, and their geniuses could manipulate you. That was all there were, or was it the Greeks, whatever. But a language limits the way you think about things. And of course, so this idea of quantum duality wasn't necessary until quantum mechanics came along. Well, of course, they know very well linear algebra of operators somehow is quantum mechanics. That's the language of quantum mechanics. But they separate a matrix from its Clifford algebra representation, which I think you're losing. And of course, there are many different geometric interpretations of a matrix, which follow from, well, basically the most important idea is symmetric and anti-symmetric. That's the key idea to understanding the structure of a Clifford algebra, as well as, I believe, this idea of a frame of an observer being a splitting of the Dirac algebra into polyalgebras and so on. But that's the thing, Clifford algebra makes you think more in geometric terms, which I think is very interesting and significant. But it is all course related. It can be expressed in different languages, but some are better than others for discussing these ideas.
Well, I don't want to sort of put words in Dr. Oshevich's mouth, with saying things, claiming that he said things that he didn't. But I always had the firm understanding that he viewed mathematics as a way of dealing with the absolute part, something that you could that wasn't related to physics, but it was sort of the foundation of physics. So from that point of view, he was convinced, I think, that taking Grassmann algebra as a fundamental algebraic language relevant to physics was a very important idea. Like this whole, in fact, one of the papers that we talked about very early on in our, like a few years ago now, was a paper by Oshevich which claimed that it wasn't really necessary to invent Clifford algebra, that Clifford algebra could be quite easily derived, given that you accept Grassmann algebra as the underlying fundamental structure, and then on top of that fundamental structure, you develop all of Clifford algebra, just by.
Okay, well, I think that's interesting, but I think Grassmann algebra only deals with the anti-symmetric part, and at the expense of the symmetric part, which is defined by a metric. But this concept,
but just as you have,
I think that's also limited in its scope. Then you're talking about Grassmann algebra, introducing new structures on Grassmann algebra, and you end up with the Clifford algebra.
but you see, from my point of view, that's exactly what you're doing in your papers, right? You start with two Grassmann algebras, and the relationship between them, this duality relationship between the two.
No, actually, what I'm doing most recently is I'm trying to say that by introducing the Lorentz geometric algebra and the so-called nilpotents, which are compatible, positively compatible, if you take that as a complex structure, that's equivalent to all of matrix algebra, all of Clifford algebra. So in a certain sense, that one idea of what I call positively correlated null vectors, you have Grassmann algebra and you have the Clifford algebra, and in fact, you have matrix algebra. Matrix algebra falls out. You can develop matrix algebra as a complex, compatible nilpotents, or as I defined as positively compatible. You don't need the negatively, you don't need that duality anymore. You just complexify it. And of course, then you can talk about what is the concept of I in quantum? Do you need I for quantum mechanics? Well, lots of people talk about that. Can you write down quantum mechanics without complex numbers? But of course, in Clifford algebra, you have many quantities which have square minus one. So the question becomes, how do you interpret these out? Which is the proper interpretation, geometric interpretation of a given element?
So, but still, wouldn't you say that you begin with Grassmann algebra? Like you're,
Well, why not begin with a symmetric quadratic form? And then you can define a Clifford algebra in terms of a quadratic form then. But actually,
but then
the
you mean,
Grassmann algebra is in there too. That's the thing. Or you start with Grassmann algebra and define the symmetric part in terms of the Grassmann algebra. So you're really aiming at the same structure of square matrix algebras over the complex numbers, really. And in fact, that's the classification scheme that's used for Clifford algebra, defining in terms of isomorphisms to matrix algebra. But I'm suggesting in this new basis, you can classify Clifford algebras in essentially a different way than it's been done up till now, using just quadratic forms and matrices of quaternions to get a new classification based on that, what I call quantum duality, which is combining the symmetric and anti-symmetric part by saying they're compatible using null vectors.
Well, I think it's necessary, I think, for you to explain to us in more detail what you mean by quantum duality. I think that's
well, it's that basic relation, AB plus BA is equal to 1, or two vectors are compatible, A1 times A2 plus A2 times A1 is equal to 1, rather than just the inner product for covec. So you define that in the algebra then, and that induces a multiplication, which is equivalent to matrix multiplication. But it's pretty strange in the calculation. I finally learned how to do these calculations where Lorentz transformations give you a representation of the symmetric group. All this is really in the last section of the paper that I've sent you now, which I've also posted on my ResearchGate page now. I should try to submit it to either ArchiveX or somewhere else, but I haven't done it. I've just posted it on a ResearchGate page now.
Sure. So did you have some slides, or did you want to?
Oh yeah, I can. If you want me to share screen, I can bring back the paper, the latest version of the paper. Then. All right,
that would be useful. Yes.
Okay, let's see if I can do that. Let's see here. Okay, I have to. So let's see here. Let me open up the thing on my website first. I don't need this anymore, I guess. And I want to open up this folder. And I want to open this. Okay, now let's see if I can get back. Okay, I'm going to try sharing the screen now. I hope it will come up. If I can find it here.
That looks good.
Okay, good. I'm getting better at this finally. Okay, if I can minimize this maybe. Okay. So that's, of course, my new title, which is a takeoff of Professor Kaufman's title. He calls his paper iterant quantum integers. I call my itinerant quantum integers. It's kind of a play of language as well, but itinerant means wandering. And of course, quantum, in a entangled state, you can say electron or anything in a quantum state is kind of wandering around until it's observed, it's wandering around wherever it's wandering. Okay, so anyway, that's the idea of itinerant quantum integers. And I like to show in this paper, only really in the last section, how I envision this relationship between this and quantum language for quantum computers. Okay, so concept positivity. Okay, so this is, of course, what I've talked about before. So I give a brief introduction here. Okay, so again, what do I mean by a quantum duality? Well, I mean this relationship. We have a basis of, say, n vectors, and if they satisfy this property, if they're all null vectors, so a1 squared equal a2 squared, they're all null vectors, and they satisfy this, what I call quantum duality, then this relationship number one is satisfied. AI, AJ plus AJ, AI is equal to 0. Okay,
So
that's
just, can I ask, just, no, the word quantum.
Oh, wait a minute. Oh yeah, what am I doing? That should be 1 there, I guess. That's a mistake. It looks like AI, AJ should be equal to 1. I don't know how that happened.
Well, you said they were nilpotent, so.
Oh, okay. Well, here, this definition, that should be equal to 1. Well, okay. Oh, no. Okay, yeah, I'm sorry. It's uncorrelated if they're equal. That means it's a Grossman. I'm sorry. Yeah. So AI, AJ plus AJ, AI equal to 0 if they're uncorrelated. Okay, so that means that they define a Grossman algebra. No, that's correct. I'm sorry to confuse it then. Okay, so but this is the definition then. A set of n null vectors, well, I call it n plus 1 null vectors, is said to be positively or negatively correlated if they satisfy this extra quantum duality condition that, and now I took your suggestion to define the inner product as a symmetric part. AI, AJ plus AJ, AI is equal to plus or minus, but really I only really am interested in the plus. So you can see if they're distinct pairwise, if they're just pairwise distinct, then it's just equal to 1. So I call that quantum duality condition. And the antisymmetric part is exactly the Grossman part. So in a certain sense, it's putting together the symmetric part with the antisymmetric part. And this is what's lacking in the ordinary concept of duality when you define it as a separate vector space. So that's where I'm trying to distinguish that. Okay, well, so this table that I'm showing you again reduces matrix multiplication to this simple rule for multiplying these basis vectors together. Okay, so you see AI times AI is 0, AJ times AJ is 0, but AI times AJ well, that's an idempotent, as we can see that AI AJ is equal to AI AJ. Okay. But if you multiply AI times AI, and of course, matrix multiplication and this algebra I'm defining satisfies the usual rules of matrix algebra. So it's associative. We have AI squared times AJ. Well, that's 0 because AI squared is equal to 0. So what I claim is that you could define everything about matrix multiplication totally in terms of this table, assuming the usual rules of matrix multiplication that it satisfies. Okay, so again, I think one of the most important points of this paper is that matrix multiplication can be defined in a different way than standard matrix column vectors, row vectors, completely compatible with those ideas, but it's a more basic definition of what we mean by matrix multiplication. And it's defined in terms of the geometric algebra 1n. And that's an important relationship here. First of all, if you start with this geometric algebra, 1n, that means you have n plus 1 anti-commuting vectors. This is called the standard basis, E1, F1 up to Fn. These E1 has squared plus 1, F1 squared equal to F2 up to Fn squared is equal to minus 1. Okay, so those are the, that's where we get the, that's the signature of the quadratic form, which defines geometric algebra 1 comma n. Now you can define this new basis, which I'm calling the nilpotent basis of this geometric algebra by using this simple definition here. Define it recursively. Okay, first of all, I define the sum of these vectors. I write as AK, I equal 1 to K of AI. Okay, so the geometric algebra, the standard, that's called the standard basis of the geometric algebra. I'm saying that really, if you complexify this geometric algebra and use this basis, this multiplication table, you define all of matrix multiplication. Now, it's true, I can show you how to get what the matrix, what the isomorphism for any geometric algebra that's been well defined. The relationship between any geometric algebra GPQ in a matrix algebra, there's well-known matrix representations of any such geometric algebra. But there's no real good way that I know of going from complexified version of G1n represented in terms of this new basis of nilpotence and matrix multiplication. There must be a better way than what I know. And like I say, this is why I believe you can classify Clifford algebras or matrix, well, classify Clifford algebra in a totally new way using this new multiplication rule that I give here. By complexifying this algebra, it's equivalent to the usual row and column definition of matrix multiplication and so on. Of course, everyone knows the relationship between linear algebra of endomorphisms and matrix algebra. That's the abstract definition of matrix algebra, defining in terms of linear operators, which are, again, that's the language of quantum mechanics, is the linear operators. And it's this relationship where geometric algebra becomes important in giving specific geometric interpretations to matrices. And this is generally ignored. Usually people pick out the Dirac algebra or they pick out the Pauli algebra. Well, Hesnes has a splitting, which I think is extremely important. Each observer corresponds to a Dirac time-like vector, which has square plus 1, and that splitting defines the Pauli algebra, namely the Pauli algebra of bivectors of the Dirac algebra of the usual gamma matrices. Okay, anyway, so this is what I'm trying to emphasize in this thing. G1n is just exactly the same thing as take the real number system and extend it by n plus 1 nilpotents, which satisfy this, any pair of them satisfy this multiplication table. And I'm saying that that's what defines matrix multiplication in its most general form. Well, you have to talk about quaternions, you know, the usual classification of matrix algebras uses quaternions. In special cases, they go to the quaternion matrices and so on. But, well, anyway, so I think I've made the point then. I'll just go on here. So anyway, this is the definition of the geometric algebra standard basis in terms of these nilpotents then. So that's important. Well, now I make the point, let's take a second basis of B's and just define each Bj as a complex, take I, that's just the usual I squared equal to minus 1 of complex numbers, and say Bj is equal to Iaj, then what you find, that you'll find these are negatively correlated. And that's what defines the what I call A minus n plus 1. So again, right, replace AI by IHA, and then do the multiplication, you'll find that that's usually I had two tables, table 1 and table 2. But now I see that this table 1 is sufficient if you just complexify it. And that's the only point I'm trying to make at this point right here. But anyway, this gives you a way of defining relating the standard bases, which consist of these anti-commuting elements, which have square +1 and then -1 across. That's what we call G1n. It took me a long time to find this canonical way of defining it, because it wasn't obvious. It was obvious that it could be done, but getting this nice canonical form was not so obvious how to find that. But really, I haven't. But I think it is very fundamental. There are other ways of defining this basis as well, but this is a nice canonical way of doing that. Anyway, I just remark here, if you take AI plus IAK, you'll get that's 2I times A. So remember now, scalars, other complex numbers here. You'll get this mixed AI plus I times AK squared is equal to I then. Well, that's something interesting. Anyway, different interesting geometric interpretations arise when considering A plus over the complex numbers. And I discussed a little more in the last section of the papers then. Okay, well, okay, so then I've showed you this before. This relates the two bases using this matrix of transition, A1, A2 up to A. So if you're given the standard basis of the Clifford algebra, you can define these nilpotents, A1, these correlated nilpotents or dual nilpotents, and this, let's say each pair are quantum duality expressed by any pair of these two vectors. And that's what I'm trying to identify in the last section of the paper with up states and down states of a quantum computer. And of course, there's much work been done using the stereographic projections. I've written quite a number of papers about relationship between up states and down states. If you just take stereographic projection of the unit sphere centered at the origin and taking these projections from the South Pole. So that's in some of my other papers, which I've referenced in this paper then. Anyway, so this relates to standard basis. They're very significant. I haven't tried to demonstrate it. Inductive arguments will give the art, but I just haven't got around to doing all the details. But this is true. These are good relationships I'm giving you here. I did have a mistake. Notice that there's only one minus sign here, and all the rest of the signs are positive down the diagonal here. So that's just the inverse of this matrix. And of course, all we're doing is, once you have this relationship, multiply both sides of the equation by T, the matrix inverse of this, and you get this relationship. So again, I'm emphasizing here that you might as well consider matrices of where the elements are geometric numbers of the geometric algebra G1n, because matrix notation and geometric algebra, they obey all the same algebraic rules. So you're enriching the matrix algebra by taking matrices of geometric numbers then. But you're using, now you have the row and column matrices. I don't violate any of the usual rules for column matrix multiplication times row matrix and all that, but now you can have elements, a column vector consists of these A1, A2 up to A8. Well, I only took 8 dimensions because I don't want to make things, you can expand this to any number of dimensions by that basic relationships which we have. This relationship is extremely important in extending the dimensions of the algebra you want to look at. Okay. Well, this is 6 and 7 are one of the few calculations which I give, and I'm just exactly referring back to this basic multiplication table here. So using that multiplication table, you can very easily everything in matrix algebra has to be proved using that multiplication table then. Okay, so define, so take any two of these nilpotents, AI and AJ, which are distinct, then that defines an element in the algebra such that E squared, okay, AI plus AJ times AI times AJ is equal to that is equal to 1, okay? But you can also define AI minus AJ times AI minus AJ. And again, using the rules of that table is very easy to show that, you get exactly that relationship that but that's for any pair of these vectors. That's the amazing thing. It's kind of you're defining a non-local algebra. It's just like, let's see, you have global property. You're reducing a global property of the matrix algebra to a local property of pairs of these basis vectors of nilpotents. And that's the amazing thing. So matrix multiplication, instead of a global multiplication, you're defining as a local multiplication between any pair of these null vectors. That's different than standard matrix algebra, but in a way it's equivalent to. So I'm saying that anything you do with matrix algebra could be done with the complexified version of this table 1. And I think that's the language, natural language of quantum mechanics, not only quantum computers, but that's what I'm trying to emphasize in the last section of this. And I think it's a whole new area which can be developed, in which I'll never be able to do. I don't know how much more I'll be able to do, but I'm certainly very interested in this strange or unusual or basis of these nilpotents, which are, I call them quantum duality of these, incorporating the symmetric and anti-symmetric part, which is missing in this usual definition of duality between a vector space of vectors and the covectors in the dual space. And of course, from now what we talked earlier, it'd be nice to understand the relationship to category theory, how these ideas relate to category theory, and maybe more specifically graph theory, which is the ideas I was originally trying to work on, trying to figure out, but somehow I got, anyway, so these are very basic. Also build your confidence in the basic nature of that multiplication table 1. That's very easy to prove these relationships. Any pair of nilpotents, distinct nilpotents, positively correlated, well, all pairs of these null vectors are quantum duality between any pair of distinct basis vectors of what I call an plus n plus 1, which is exactly in the standard basis, the geometric algebra G1n. You complexify it, multiply by I, you get my table 2, but now I'm not really interested in that at all because I recognize it as just, it's just taking the imaginary number I times, but there's many other things that anyway, these are very basic relationships. Okay, well then we can define, furthermore, these orthonormal vectors E1 and F are anti-commutative, okay? And that's very easy to prove. AI times AJ, A minus AJ, multiply it out using table 1 again, you'll get that's minus FE. Well, that's what we call a bivector. And this bivector will have square plus 1, okay? And I call them the seed vectors. Once you can choose any one of these, AI and AJ, it doesn't, again, we're reducing global properties of a matrices to local properties of 2 basis vectors. Any 2 basis vectors in this basis of nilpotents can be chosen to determine this E and F, and then you use, okay, E and F, and then you have all the rest of the relationships defined by this basic relationship here then. But of course, it doesn't matter what order you choose them. And again, so in a certain sense, these are local properties, defining matrix multiplication in terms of local properties rather than multiplying column vectors and row vectors of arbitrary length. Okay, so I see it as a different way of defining matrix multiplication. Okay, here you have a calculation showing EF, they're orthogonal, orthonormal vectors, which have square plus 1 and minus 1. Okay, now this is an important idea as well, what I call the canonical basis of this algebra, or the real numbers consist of elements of the form 1, A1, A2 up to AN plus 1. Those are the null vectors correlated, or let's say any pair of quantum duals of each other. And then you have the pairs of these things, take all pairs of them. But notice that they're not orthogonal to each other. All pairs of these things define idempotence. Again, very basic concepts in quantum mechanics, the notion of an idempotent. And in fact, any three of them define the usual geometric algebra of space, of the Pauli algebra defined by any three of these vectors. So you see the algebra of space, or geometric algebra G3 of Euclidean space, is defined by any three of these nilpotent elements. And of course, that's where the idea of stereographic projection on the unit sphere and all that. I try to discuss some of these ideas when I talk about the Pauli algebra. Okay, anyway, so what is the canonical basis? Well, the canonical basis is when you write down an element, the product of, say, k elements, you put them in, you satisfying A1, lambda 1 less than lambda 2 less than n to k less than n plus 1. You keep them in that order. So that's called a canonical basis. Okay, and I then introduced the standard notation. A lambda 1 is the product of these. Now it's, you see, if you take the outer product of that, you get the K Grossman element. But that's a mixture of all these types, because remember, these are not orthogonal vectors. They all satisfy the property A1 dot A2 is equal to 1/2. AI dot AJ is equal to 1/2 for any I not equal to J. So again, that's a universal property, a local property that all these nilpotents satisfy.
Can I ask about that equation 9 there? What's the meaning of the 1 as the first element of that?
Here?
Yeah. No.
Why do I put n plus 1?
No, why do you put 1 comma?
Oh, well, that's that's the usual real number system. I say over the real number system.
But you said these were vectors.
Well, they're not really all, these are vectors, but these are products of vectors and products and so on. That's like writing a basis of a Clifford algebra, starting with 1, E1, E2, E3, E1 times E2, E1, just the usual. So I am
Okay. So maybe I'm a bit confused because check equation 3.
Okay.
The point there at equation 3. That's the same symbol. You say a set A plus minus.
Yeah.
But there's no 1 there.
Well, that's right. But I'm saying this generates, just like if you take in the standard basis, okay, remember, if you take in the standard basis E1 squared, that's equal to 1. So I consider that the zero element, okay, is 1. The generators. So for the whole algebra, but again, here you go. Where is that this basic relationship? I say it's generated by that set, okay? Well, let's see, where is that basic relationship? Oh, right here, look. Okay, you see, it's so my basis consists of the generating basis consists of those vectors alone, A1, A2 up to AN plus 1, and their products and so on. And of course, E is equal to AI plus AJ squared, then is equal to 1. So the real number system, I'm taking this algebra over the real number system. So it's in there.
Yeah, maybe my question is just typographical then, like in equation 9, you use the
Yeah.
same
Well, that's
symbol.
right. So I'm saying that any element in this algebra can be represented as a linear combination of these 2 to the n plus 1, 2 to the n plus 1 elements. And that's just like in the standard basis, any element of the geometric algebra G1n can be represented as a linear combination of the standard basis, which is 1, and then the vectors, and then the bivectors up to the n plus 1 vectors. But this is really a mixture. Well, okay, you have 1 and you have these null vectors, n plus 1 null vectors, then you have these products of all pairs of them, A1, A2, A1, A3, and so on. You still have 2 to the n plus 1. This is the standard basis, then I'm calling it the standard basis. But if you wrote it in terms of the standard basis of G1n, then you have 2 to the n plus 1 elements in terms of the standard basis. But this is a different basis of the same geometric algebra 1n, and it has, as a linear combination, it has 2 to the n plus 1 elements. But for example, well, then I show you a multiplication table for, we've seen that before.
I think my comment was somewhat simpler. I was just trying to understand the notion of that your symbol, a plus a superscript plus a subscript n plus 1. That
Okay, I should define, maybe I should define that 1 as A0, well, just A0 equal to 1.
But
that's
no,
a
I'm not worried
scalar.
about that. I'm just thinking about this notation, a superscript plus subscript n plus 1. And you appear to be using that notation differently in 3, point in your equation 3 compared to your equation 9.
Now, there might be a problem. I don't know. Let's see. 3.
Yeah, so you
Well,
say
no,
you
in
have,
this case, AI and AJ run between 1 and n plus 1 here. So I'm
But
not
you've
defining, these are not
But you've
real,
written
these are vectors, null vectors.
but you've written a superscript plus minus n plus 1, but this a superscript plus is something different than this, right? You said,
Well, I'm saying this is the basis element. The null vector basis, it's the generators of the same geometric algebra as a standard basis. Okay, the standard basis is this basis. Okay, but when we write down the generators consist of just the basis vectors E1, F1, F2, F3 up to Fk or Fn. Okay, that's a little confusing of the notation. I take k going from 2 up to n because I have n plus 1 elements. Okay, I take a1 up to an plus 1 because of that. Okay, that's most people don't do that. I use the fk goes from 1 up to n, and most people use the e1 up to en plus 1. Well, for the standard basis, but then they have to distinguish what has square plus 1, what has square minus 1. I distinguish that using a vector the basis vectors f1, f2 have square minus 1. I'm leaving vectors which have square minus 1 with a different symbol than the vectors which have square plus 1. So GPQ has P vectors which have square plus 1 and Q vectors which have square minus 1. So I would denote them by F1 up to FQ and E1 up to EP, okay? But a lot of people just define the standard basis of the geometric algebra GPQ as E1 up to EP and then EP plus 1 up to EP plus Q. But I like to distinguish between the symbol representing vectors which have square plus 1 from those having square minus 1. But all these vectors are anti-commutative. And the geometric algebra G1n is generated, I'm emphasizing that, by taking the real numbers over A1 up to AN plus 1, okay? Because the standard basis consists of n plus 1 elements, E1 up to F goes up to N. So I can see where the confusion arises. I've confused it myself, but I think I have straightened it out here. I don't think there's any contradiction now. Does that help?
Yes, for now. Thanks.
Okay, so again, the vectors are the generators of the algebra, and we saw in this relationship here that taking as generators, if you take the element E, any pair of them, square it, you get the real numbers. So the real numbers is in the algebra generated by taking multiplications, with the multiplication being defined again by this very basic table. This is local. For any pairwise, you're defining it as a local property of any pair of these null vectors, which is the unique property of this algebra. So the whole algebra is defined locally in terms of this table over the real numbers, which generate the algebra 1n. And if you take pure imaginary I in front of all of them, then you get the other algebra, which I was calling A minus n plus 1. But I only really want to look at A plus over the complex numbers, and I claim that that's isomorphic to the usual matrix algebra of generated by n plus 1 squared matrix algebras. And, well, okay. Okay, let's go down then. Okay. Okay, so now I'm just trying to give a simple example. We start, okay, so when I'm changing my notation, I'm calling them quantum numbers or quantum integers. Okay, so we define, so instead of writing, always tagging on A1, up to AN plus 1, and so on, A lambda 1, I just use those numbers themselves. So, for example, A6 is generated, so by 1 hat, I mean that's A1. 2 hat means A2. 6 hat means A6, but I'm dropping the A's. What's really important is only the indices. So why keep the A's? So, and that's really a trivial generalization. It doesn't really change anything. It's a different notation for the A1, A lambda 1 up to A lambda n. I'm calling those quantum integers. So A6 is defined in that way then. Okay, now, so that's what I want to do here. I want to define, for example, full canonical basis for n plus 1 equal to 3 over the real numbers. So the algebra is generated by the real number 1. Okay, these are generated over the real numbers. So any algebra, any number, in the algebra A3 plus, which is the same thing as G12. That's equivalent to it's just a different basis for the geometric algebra G12, okay? Consists of a basis, instead of writing E1, 1, E1, F1, F2, E1, F1, E1, F2. I'm just writing now in terms of this new basis, but notice that these are not orthogonal elements. With the standard basis, these would be bivectors, but now it's a mixture of things. Okay, so we have 1, that's just the real number 1, the identity element. And then we have the quantum integers, what I'm calling quantum integers, which before I was just calling A1, A2, and A3, A1 times A2, A1 times A3, A2 times A3, A1 times A2 times A3. But now, okay, I do a couple of multiplications here. Okay, what is this? Let's reduce 1 hat, 2 hat times 3 hat and see what we get. Well, we get this. If that product represents 1 hat minus 2 hat plus 3 hat minus 1 hat wedge 2 hat. Again, you can read that in terms of the A's. That would be A1 hat times A2 hat times A3 hat equals A1 hat times A2 hat dot A3 hat plus A2 hat wedge A3. I'm just dropping the A's, but I do distinguish between 1 and the quantum integer 1 by putting hats on that. Well, I use hats for a lot of the notation, but okay, but this is the interesting thing. I've shown you that already, but I think it is a multiplication table. It shows you how, again, this multiplication table follows from table 1 that I gave at the beginning of the talk. You can flip back there very easily, of course. Right there it is. So all that multiplication table I'm using, it follows from this basic table 1, local definition of matrix multiplication, the equivalent of a local definition of matrix multiplication. Okay, let's go back to that. And now you can see why I'm talking about the canonical basis of this algebra A plus n plus 1. Because if you put it, if you look at this multiplication table, so all these numbers, 1 less than 2, 1 less than 3, 1 less than 2. If you remember, you checked me on that, I didn't have all the things reversed. So you see, the element represented by 1 hat, 2 hat times 3 hat is really the difference of two bivectors. Remember now, 1 hat dot 2 hat is 1/2. 1 hat dot 3 hat is equal to 1/2 because that's a local property of all these quantum integers. So you can see this is a pure bivector. 1 hat 2 hat minus 1 hat 3 hat is the bivector A1 wedge A2 minus A1 wedge A3 because the scalar part drops out. Okay, so that's really a bivector. But you see, that's what if I multiply 1 hat, 2 hat, 3 hat times 1 hat, I get this bivector. Or 1 hat, 2 hat times 3 hat times 2 hat. Well, notice we have 2 hat, 3 hat, 2 hat, and that's just 1, 2 then. Because remember, 2 hat, 3 hat, 2 hat from that table 1 is exactly what we have. I'll go back again. I want to emphasize the importance of that table. Okay, so here you have it. AI times AJAI. Remember, AI and AJ are distinct. AI times AJ times AI is AI. Well, that's okay, because I have AJ, no, AI, AJ, AI. AJ is in between AI on this side, AI on this side, you get AI back, okay? Which is unusual. You see, that's standard definition of duality don't give you that, okay? And that's what's extremely important in this new local multiplication table of matrices, which I'm defining. Okay. Okay, well, I do some calculations here. That's all I do. So I think I've got all that right now. I corrected the errors before. You see 2 is less than 3, 2 is less than 3, 1 had, they're all in canonical order. That's why I call it a canonical basis. Okay, I also define the order.
You still have one that's not in that sequence.
Where's that?
Second one from the bottom in about the middle. Your cursor right there, 2, 1.
Oh, that's correct. That should be okay. Yeah, that's right. Okay, so that should be. We can easily fix that. Of course, we fix it by, again, remember, 1 hat 2 hat plus 2 hat 1 hat is equal to 1. So we easily fix that. Then I'm sorry. This table, multiplication table, but you're right. I should change that. This is correct, but this should be written as. This should be written as what? It should be. Well, you can remember A1 times A2 plus A2 times A1 is equal to 1 is equal to 1. So A21 is equal to 1 minus 2. Okay. Well, you see like this one. Okay, look. Okay, look, 2, 1. Okay, what is 2, 1? 2 times 1 is 1 minus 1, 2. Okay, that's so I should change that. Replace 2, 1 by 2 times 1 is 1 minus 1 hat 2 hat. Okay, I didn't notice that. Okay. So you can easily fix that. And again, I go through a couple of multiplications here. I reduce this one down. I just do several multiplications to convince you that I'm just using that table 1 to reduce all these things to canonical form. It's got to be in the canonical form, which I've made a mistake here then. Okay, well, I wanted to find the squares of these things. The interesting thing, if you take this, now if you take a trivector in this algebra, it has square -1. But if you take just the products, 1 hat, 2 hat, 3 hat, and you square that, you get minus 1 hat times 3 hat. So again, if you write, you can write that 1 hat times 3 hat, 1 hat times 3 hat, well, it's just 1 hat, 3 hat, that's the canonical basis. But if you take 2 hat times 1 hat, you get this, or 3 hat times 1/2, you can see 3 hat times 1/2 is 1 minus 1 hat, 3 hat, because 1 hat, 3 hat plus 3 hat, 1 hat is equal to 1. That's the duality, quantum duality, by quantum duality. Okay, I'm just doing these calculations. I hope they're right. It can be extremely confusing. I've written many pages on screwing it up. There should be a computer program that does that with mathematics, but I haven't done that. That's I'm not so good at mathematics. I'm pretty good at it, but I haven't, well, there's just too many things to do. But anyway, I take it up to n plus 1 equal to 6. That means n is equal to 5, of course. And I try to do the calculations. I think this is correct. If you reduce this to the canonical basis, I hope, I think it's correct. 1, 2, 3, 4, 5, 1, 2, 3, 6, 1, 2, 4, 6, 1, 3, 4, 6. So that is properly represented. But you can see that's a mixture of all kinds of vectors and scalars, vectors and bivectors. If we put it in the standard basis, it would be vectors plus bivectors plus trivectors. But this is a mixture of everything because it's a local representation of the matrix product, not globally. So that's why I think it'd be interesting to classify Clifford algebras all in terms of this new types. Okay, well, this final section, which I call future research, the most interesting issues of the rise in quantum mechanics is a crucial role played by imaginary numbers I equal to -1. Many papers have been written suggesting, sometimes even, quote, proving that it's impossible to formulate quantum mechanics without complex numbers. In Clifford geometric algebras, many geometric quantities arise which have square -1, okay? Like most famous example, like I try to talk about the polyalgebra here, is a geometric algebra G3, sometimes referred to as biquaternions. Biquaternions are algebraic and isomorphic to famous polymatrices, complex polymatrices again. So, okay, quantum mechanics, G3 imaginary number I takes on the geometric significance of an oriented 3-dimensional volume element called the trivector. Okay, that's the Grossman. So again, we're putting together the symmetric part and the anti-symmetric part for this local definition of matrix algebra. That's the whole idea. Unit trivector 1, 2, 3 is in the center of the algebra, but this geometric algebra G3 is not the same thing as a geometric algebra 1, 2, because a geometric algebra 1, 2 is generated by E1, F1, and F2. So in this section of the paper, I'm just trying to point out, again, the relationship of these geometric algebra. When they talk about matrix isomorphisms, you're really mixing up the notion of bivectors with vectors, which is done with again, using the Dirac algebra and the Pauli algebra, very important algebra. That's, of course, very important that in physics, those are two algebras, the Pauli matrices and the Dirac matrices, are crucial for relativity theory, quantum mechanics, and so on. Well, but I'm emphasizing that this algebra A3 plus is really a property of AN plus 1, okay? Because any three of them define the geometric algebra, but again, you have to use this twist. We can only say that the geometric algebra 1, 2 is isomorphic to the geometric algebra G3. So there's many things that one needs to think about. But what I can say is that G1, 2 is generated by the real number system extended by 3 unit orthogonal vectors, E1, E2, E3, which all have square plus 1 and anti-commute. Okay, but we can say that that algebra is isomorphic to E1, and then I take, remember, I'm identifying I now is equal to E1 times E2 times E3. So I'm identifying that as E1, I times F1 minus I times F2, and that's the geometric algebra 1, 3. Oh, but
Looks
this
strange.
is my mistake. I should have written 3 here. That should be a 3. Okay, I'm sorry. I have to fix that. Okay, mistake on page 7, I guess, right? Page 7. G1, 2 equal to R E1, E2, E3. I need to pick that up, okay, because I missed that. But you can see that anyways, and it's just a typo. I'm just emphasizing this relationship, how you get this isomorphic to the matrix algebra, which we know very well. So that should be G3. That's real number system, the way I look at it, extended by E1 times E2 times E3. But that's isomorphic to this. But that's isomorphic to this, which is G1 through that. But that's another mistake. That should be 1, 2 here. I'm sorry. So that's 2 mistakes. Okay, I've got to fix that. That's awful. Okay, page 7 again. I have to fix that. That's bad. That should be G1, 2 there. So G3 should be on the left. Okay, I'll emphasize that. So again, that should be replaced by G3. And this should be G1, 2 on this side, okay? I don't know why. Again, you just get tired or whatever, and you make such mistakes. But I think it's, okay, it's just a mistake there. Okay, I'm sorry about it. I try to go through this stuff, and it's just hard to get all the bugs out. Okay, anyway. This demonstrates that quadratic form determining the metric of a geometric algebra is inseparably tied up with the property of anti-commutativity. In the geometric algebra G3, the metric is determined by the anti-commutativity of E1, E2, and E3, whereas the metric of the geometric algebra 1, 2 is determined by the anti-commutativity elements E1 times F1 times F2. Well, unfortunately, that doesn't help making that mistake there, but you can see what I'm trying to say. So more is involved than just saying these algebras are just isomorphic, not, when you look at the matrix algebra level, in terms of the geometric algebra, it makes that distinction clear. Well, again, that's one reason why people don't want to look at this stuff, I guess, because matrices have many different interpretations. If you look at the matrix of the algebra GPQ, well, that's called, the periodicity 8 of geometric algebras, which are studied very nicely by Lunesto and a number of other, Porteous, for example, all have those relationships. It's another name for it is a bot something relationship between periodicity 8 of geometric algebras and so on and so on. In Einstein's special relativity, this dichotomy reveals the underlying structure of space-time itself, and hence the space-time algebra, the Dirac algebra of gamma matrices is a matrix equivalent of the geometric algebra 1, 3, which is, this is correct, A4, and I give references. For example, each time like Minkowski vector gamma 0, which we represent here as A1 plus A2, determines the rest frame of an observer. Okay, but any pair A1, A2 determines a rest frame. Well, all you need is a Dirac algebra, but okay, but I'm actually want to go to any number of dimensions, AN plus 1, and that's what I'm talking about when I talk about the symmetric group. Okay, well, I try to emphasize that. The geometric algebra of the observer of the rest frame determined by gamma 0 is equal to GR extended by E1, E2, E3, where in this case, we're interpreting gamma 1 times gamma 0 as a vector, E1. So these are bivectors in the Dirac algebra. This is called Hessian splitting of an observer of the Dirac algebra. And that's what we call G plus the even subalgebra of the Dirac algebra, 1, 3. Okay, that's correct as well. Oops, did I make a mistake there? No, that should be 1, 2. Okay, again, 3, 1 plus 2 is, that's a, oh, wait. Yeah. Yeah, well, no, this is correct. This is, yeah, that's the subalgebra of G1, 3. That's correct. There's no mistake there. Again, it's easy to get confused. Okay, is that clear? So again, E1 is a bivector in this Dirac algebra, 1, 3. The even subalgebra. So the bivectors are F1 times E1. They have square plus 1. E2 is F2 E1. E3 is F3 E1. So this is correct. Nothing wrong with this at all. Where gamma 0 is E1, gamma 1 is F1, gamma 2 is F2, and gamma 3 is F3. Okay, so that's in the standard basis of the Dirac algebra, G, what I call G1, 3. Okay, that's the, yeah, the Dirac algebra is G1, 3, and that's gamma 0, gamma 1, gamma 2, gamma, that's isomorphic to the Dirac matrices then. And I give references there. There are two very interesting, okay, this is extremely interesting, which I only discovered in the last week, but it's very basic, and it caused me a lot of trouble not recognizing this because the calculations in that algebra become unwieldy, but this simplifies things tremendously and makes it very beautiful, actually. There are two very interesting representations of the symmetric group S, n plus 1 that can be found in A, n plus 1 plus. And I give a reference. It seems natural to identify a qubit as a pair of compatible null vectors. The upstate of the qubit, their sum, and the downstate being their difference. Well, again, that goes back to that basic relationship when I defined E and F, because that's a local property, though. The maximum quantum element of order n plus 1, again, order is different than the degree of a Grossman element. The degree is determined by the outer product, whereas the order is determined by the number of the nilpotents in the canonical basis, okay? So the order of order n plus 1 in the canonical basis of A n plus 1 is this element I define n capital is 1 hat up to j hat, k hat up to n plus 1, okay? The 2-cycle jk, which interchanges the quantum integers j hat and k hat and n hat is specified by, and I'm denoting it by the symmetric group operating on this element, the element of maximal order in the canonical basis of an plus 1. Okay, that's the product of all these. That's a mixture of all kinds of vectors, bivectors, and so on, if you write it in terms of the standard basis, or just expand all these things out. Anyway, so this is the action. You can get it by taking minus j minus k times n hat times j hat minus k hat. So multiplying on either side of n hat by this element, which has square minus 1. Remember, we saw that in the previous relationship. All that does to this thing is it interchanges those two elements. I was always, in fact, in that multiplication table I gave you here is extremely confusing. You can see if you multiply that out and put it it's extremely confusing to go through these multiplications, which I suffered. I don't know how many hours trying to get it right. But with this thing, you can define the operations on the symmetric group. Okay, where am I at here now? Okay, let's see here. Okay, here we are back. Just as that's a Lorentz transformation. Okay, remember, double covering. The Lorentz transformation is a double covering of the Dirac algebra, or the Lorentz trans boost and rotations and so on. Well, so we're using a double covering of the group it's the same group generated by the algebra of nilpotents. So that's a representation of the symmetric group, which Professor Kaufman generates by using an external structure, because again, he uses the standard notations of mathematics, and he doesn't have the quantum of what I call quantum duality, which makes it so you can represent all these relationships locally as properties. The symmetric group takes on any cycle of the permutation group, JK, can be represented as a Lorentz transformation acting on this maximal quantum element. All that does is changes the order of the, so if this is in the standard basis, n hat, then it interchanges only those two null vectors, leaving all the other ones unchanged. Well, I don't prove that. I believe it's true because I've calculated more than once, but I wanted to get this done because I'm taking a trip on this Thursday, and it just doesn't give me any time, but I wanted to have something posted before we left on our trip this Thursday. So anyway, I posted it. But that's one representation. We have a second representation of the symmetric group in AN+1, represented by triplets of positive quantum integers acting on the quantum sums of pairs of these things. And the only difference here is that, it's a little differently. In this case, remember I tried to say that the sum of these elements is in some sense a duality type relationship. So in this case, what I'm doing, I'm taking I hat minus j hat, operating on j hat plus k hat, I hat minus j hat, and what it's doing, it's interchanging, it's changing the j into an I, okay? And what I call passive Lorentz transformation, double count, okay? And then I give the other ones as well. So this is equivalent to saying 1 hat plus 2 hat goes into, okay, what am I doing here? Okay, I'm identifying those. See, where am I think I introduced that notation. Okay, let's see here. Okay, so what I mean by 3 hat, I'm making this comparison here. You see, I'm saying that 1 hat, 2 hat corresponds to 3, 2 hat, 3 hat corresponds to 1, and 3 hat, the sum of these quantum integers corresponds to 2 and 3. So when I write down this pair in the cycle, the 2 cycle, 1, 2, okay, and this first one, okay, what am I doing? Okay, so this is interchanging the pair JK of this maximal quantum element of the product of all of them, whereas this one, we're only take any 3 pairs, I hat, j hat, and k hat, and correspond 1 hat plus 2 hat with 3, 2 hat, 3 hat corresponding to 1. Okay, and then these things are representing those cycles, 2 cycles specified by 1 hat minus 2 hat goes to 1 hat, 3 hat, which corresponds to 2 hat, okay, and so on. So this is an equivalent way of representing the symmetric group on n+1 elements in terms of 3 2-cycles, which generate the symmetric group as well. So I call it 2 distinct ways of representing the symmetric group. Well, again, much more can be written to clarify these ideas, but I just didn't have the time. But I try to give a summary. In view of 17 and 18, it seems natural to identify a qubit with a pair of compatible null vectors, the upstate being their sum, downstate being their difference. It also appears that double covering Lorentz transformations can be used to find various local gates. 5, 6. I reference Dr. Havel's papers that he wrote with Chris Doran, Dr. Doran's papers, early papers on quantum gates or logical gates written in terms of geometric algebra. They have a paper where they try to represent quantum gates in terms of geometric algebra. So I think that's an appropriate reference there. And that of Professor Kaufman's. I've chosen that my title, Itinerant Quantum Integers, Language of Quantum Computers, rather than using Professor Kaufman's itinerance and the Dirac equation. Well, it's related. These ideas are, I think, are clearly related by the references that I give to his papers. Finally, it's important to remark, whereas all Clifford geometric algebras GPQ are isomorphic to real, complex, or split matrix algebras, it is equally true that all geometric algebras PQ are isomorphic to real, complex, or split quaternion algebras, where n+1 is equal to P plus Q. Okay, well, this is my idea that table 1 is a local definition of matrix multiplication. If you take that complex algebra, it's really equivalent to matrix multiplication. But and that what would clarify that idea is representing the isomorphism of these general geometric algebras in terms of this new definition of what I call local definition of matrix multiplication. The author believes that this preliminary work will find many applications to theoretical physics, representation theory, many other areas of science and engineering. Perhaps most importantly, it will become the language of quantum computers. The word itinerant means wandering. Perhaps this word captures the spirit of quantum integers and the mysterious nature of entanglement, which makes up quantum mechanics. Now, in reference 26, I give a reference to a paper by, well, actually, it's Zeilinger's paper, Nobel Prize winner, an interview with him, which is very interesting. Discovered can make measurements, but cannot say anything about the essence of reality. Very interesting papers, and tries to emphasize this relationship that I'm trying to express here. So that's basically a summary of which this paper is posted on. But again, I'm glad you pointed out, I still have a couple of, but it's only a preprint, so maybe people will forgive me. Some of the earlier things I posted are much, for example, at first I tried to compare this idea to graph theory, but now I think the closest comparison, most clearly comparison is to quantum mechanics, but all these things we've been talking about, category theory and graph theory, I think needs to be clarified. And that's, of course, what I hope that we can continue in that direction as well. But it seems to me that this seems to me it's pretty exciting new way of looking at matrix multiplication in terms of a local definition of the matrix product rather than huge matrix multiplication defined on, I still have n+1 elements, but now it's a local definition of table 1, which I'll highlight again, that defines a local multiplication of these elements using basically the same rules of matrix multiplication. Right there, that characterizes matrix multiplication over the complex numbers. That's what I claim is equivalent to matrix multiplication. Okay, so that's about all I can say, I guess.
I'm in that, given that multiplication that you just showed, um, I, I think it might be interesting to see how that particular multiplication relates to this algebra of iterants that Kaufman talks about.
Well, that's right. That's exactly what I'm trying to do in the last section of the paper. By referencing his papers, it's clear in fact, that's what inspired me or convinced me I needed to see how to represent the symmetric group. That's exactly what he's doing in one of these papers, which I reference his papers there. Let's look at his references that I give here. I forget. Okay, I think maybe it's construction. Okay, here, this 9 and 10. He's doing a construction of Clifford algebras using this we call it iterant representation, and that's actually where he constructs the symmetric group. Well, that's what made me consider, how does he get that, or what's that? Well, that's what I'm able to do without leaving the geometric algebra, which he introduces an additional structure outside of the geometric algebra to get that representation. And then he shows that Clifford algebras can. So in a sense, you can say my work is another way of looking at his work. It's a different way. I think it's worthwhile making the distinction in the title. Instead of using iterant like he uses, I use itinerant. But it's in a certain sense, it's doing exactly what he does, and he does many more things in Majorana fermions and Majorana Dirac equation and so on. Whereas I compare my work more to Hessnies' work because that's what I'm most familiar with. But certainly, I would suggest that there's an extremely close relation. He's talking about Grossman algebras here and matrix algebras and the symmetric group, how to represent them in what he calls itinerants. But again, he's emphasizing a structure outside the Clifford. Well, he's defining Clifford algebra in terms of this outside structure, whereas I'm actually turning it on its head and defining all these other things in terms of the internal structure of this new nilpotent basis, the ideas of the geometric algebra 1, n. But the ideas are obviously closely related.
But is that, so you view this definition of nilpotent basis as a construction in Clifford algebra?
Yes, because that's what I give. In the first relationship, I relate the standard basis of the geometric algebra to this thing to the standard basis by this multiplication table. So it's defining exactly the same geometric algebra that E1, F1, that's the standard basis of the geometric algebra G1N.
But when you start your paper, you don't, right at the beginning, like if you go like, yes, right in here.
I tried to refine this a little from the earlier representations to try to put it more.
But at this point, you're not talking about Clifford algebras as such, right?
Well, that's right. I'm not. I say they're uncorrelated if they satisfy this relationship. Well, that's what defines the Grossman algebra. And now I try to be careful. Okay, instead of uncorrelated nilpotents called null, generate the Grossman algebra, okay, and generate this if their outer product is not equal to 0. But now in this relationship, that's where I try to sneak in the extra symmetric properties of the dual, the standard concept of a dual. Okay, so I try to be very careful here. A set of these null vectors are said to be, so really I'm introducing additional structure on the Grossman structure, but I'm sneaking it in a way, satisfy the extra quantum duality condition. That's where I'm saying, let's define a new take this Grossman structure and define quantum duality condition where it satisfies this with an inner and outer product, the symmetric and antisymmetric part. So it's really tying the quadratic form part, which I used Dr. Page's idea that let's define the Clifford product in terms of that first, rather than I had it turned around the other way. That's more basic. But that's really where the Clifford the symmetric part is being defined then. The inner and outer products defined by this then. So you see that they're really compatible.
That still seems to me to be defining Clifford algebra from something external.
Well, it's external to the Grossman algebra. It's a new relationship defined on the Grossman algebra. The Grossman algebra doesn't say anything about the symmetric part. So it's free to define in any way I want. And by defining this quantum duality condition, then that all of a sudden the Clifford algebra pops up then. It's all Clifford algebra, all matrix algebra, square matrices. So that's the local definition of a Clifford algebra or a matrix algebra. Matrix multiplication could all be defined, I claim, in terms of this. Start with the Grossman algebra. As you know, Grossman spent most of his life thinking about, he was disappointed that it was never fully recognized as being as important as it is in mathematics until the end of the 19th century. And then, well, we claim, Estes and I always said, it should be part of the real number system itself. You know, the definition of direction, extending the real number system to include the concept of direction. And that's, of course, I'm trying to show how this is really a local definition of a Clifford algebra, I guess, rather than the standard. Well, you know, the standard, everyone always talks about Clifford algebras are consistent because there's an isomorphism to matrix algebra. Well, I'm turning it on its head now and trying to look at it slightly differently and saying, hey, look, we can define matrix algebra in a totally new way. Well, again, that's why I emphasize these definitions here. So start with a definition of a Grossman algebra. All we have is a Grossman algebra in this first, okay, uncorrelated nilpotents satisfy this relationship. No, you'll agree that that's just Grossman algebra, nothing more, nothing less, and identify that with the outer product of those vectors. So that determines the grade. That's a grading of the determines a grade or a degree of an element. But now I get the Clifford algebra by introducing what I call a quantum duality condition. So we say that if instead of just satisfying this property here, we say we make the symmetric part satisfy this relationship. I don't change the antisymmetric part. That still satisfy the antisymmetric part. Well, I have to be careful what I'm saying here. So that means that's identifying the Grossman algebra. But now, yeah, so I actually, it's a little confusing here what I'm doing, because now I'm saying, well, okay, I leave them to be actually the nilpotent parts by saying these are nilpotents. That's what really is where the Grossman structure is struck in here. Okay, the fact that ai.aj is 0 for I not equal to j, that's where the Grossman, but I'm defining it locally in a way. Well, anyway, this is, you know, I agree. This is it. So the way I'm thinking about it, so the Grossman part is just this part, okay, but then additional structure by sneaking what I'm calling quantum duality, that's where the local definition duality condition comes in, and that's why I'm calling it quantum duality. Anyway, that's what you see. But then I do say, okay, so 2ai a wedge aj is just equal to the antisymmetric part. So in a certain sense, it only takes 3 of these vectors, a1, a2, and a3, to define the Pauli algebra and the Dirac algebra. And that's extremely important in physics. That's the most important two algebras in physics, I believe, right? But this is really much more than that now, because we get all of matrix algebra as well. Define locally any three vectors, local properties of any three vectors, AI, AJ, AK, define everything that you need in matrix algebra plus table 1. So it's, again, I believe it's closely related to what Professor Kaufman has done, and that's why and that's what's interesting, of course, with this, the Spishikovic Memorial Conference that we had, and this book now of papers, which are being, I think the main editor is Professor Kaufman, if I'm not mistaken, but I don't know what's been happening lately. I guess Professor Dr. Cruz could mention what's happening with that new book that's coming out. I hope is going to be coming out with that Professor Kaufman is editing or something.
Yeah. Okay.
I have here a question, because I can understand here how do you are using the terms duality. Because in the past page that that you were showing to us, I can see the symmetric and anti-symmetric part of one product, but those are not dual.
Well, it's not ordinary duality, certainly, but ordinary duality is defined on two different vector spaces, where this is defined locally in the same algebra. Any three elements in this algebra, in this null vector basis, defines what I call quantum duality. So the fact that they're null vectors is very important. Otherwise, it doesn't work.
Because vectors algebra have two parts in the product that are the symmetric part and anti-symmetric part.
That's correct. That's right.
And then those are part of the same product definition. And because this I can understand the term.
That's what I'm doing, though. I'm replacing it by a local property that any three vectors satisfy. And I think that has to be emphasized to understand this properly. So I'm not taking all of them together. So that's right. Here I say they're uncorrelated, but now I'm introducing a property on any three vectors. You kind of think about it that in terms of that last relationship of representing the symmetric group in terms of any three vectors, AI, AJ, AK, which are distinct. That's enough to get the properties of symmetric group represented in it. So I think that's what I would need to emphasize more. I'm sneaking it in. I'm a little bit sneaky here with this property 3, and I agree. It's really only meant to define it on any three elements rather than, because otherwise I can't, I say they're uncorrelated. Any three of them are uncorrelated, put it that way maybe. But any three of them satisfy this relationship, maybe not, maybe that's I should change this property 3 to say any three vectors are related by this. That would be better to replace this definition 3 by saying a set of n+1 vectors are said to be positive and negative if they satisfy, if any three of these elements satisfy the extra quantum local quantum duality condition that AI.aj is equal to that for any three of them. Okay, that I think will solve this problem, that there is a problem with 2 and 3 sticking them together, which I basically ignored at this point.
Yeah, because I remember the definition of duality starting with quadratic forms. Then we can find one algebra for vectors and one algebra for covectors that are in different space. And in the vector algebra, one can find the Clifford product that have one part symmetric and one part antisymmetric. And then in this way, when we speak about one algebra of vectors, we are either in the same space, and then the duality is not present here.
Okay, that's very interesting what you're saying. So that's right. Duality, ordinary duality consists of a property of two vectors. But what I'm calling now, but I think that that's exactly correct. So what I need to modify three to say we say any three vectors are quantum duality condition holds for any three of, so it doesn't involve just two vectors. Two vectors, it's just the ordinary property. And that's what I show in 4. The inner product of any two vectors gives you the usual.
But why three vectors are duals?
For quantum duality is that any three vectors must satisfy 3. I'm not saying anything about all of them. That would be something that would have to be proven.
The definition that you are putting here are because one of them are a b-vector. Then this is a vector outside of the degree of the other two. This is the meaning of the quantum duality?
Well, I like to, you can look at the Grossman algebra as just being the Clifford algebra with a 0 scalar product, the quadratic form identically equal to 0, and then it reduces to the Grossman algebra. But here, actually, it looks like what I'm calling quantum duality really depends locally only on properties of, but we have to choose null vectors. That's an important ingredient of this. We're choosing only null vectors. So a local property of any 3 vectors, which define the Dirac algebra and the Pauli algebra, is related by this property, and then prove that the 2 and 3 are consistent in their more general relationship for an n vector in Grossman algebra. So, but I'm saying you can add this extra quantum duality condition in the algebra. You define duality in the algebra itself rather than having to go. Ordinary duality defines a separate algebra, whereas this one is a local definition. You don't have to go. You don't go out of the algebra. Maybe you can't even do. Well, you might get into trouble if you consider it as a global problem. I don't consider it. Well, anyway, these things 2 and 3 needs to be studied in more detail, more systematically than I've been able to do that to this point.
Let me see if I can understand Dr. Cruz's comment. Like he's focusing on the word duality, I think, and if we would agree that if you have a concept of duality, then you can, for any particular element, you can ask, what is its dual? Right? So you choose an element and you define its dual, and then this operation of taking the dual is an involution in the sense that the dual of the dual is the original, right?
Mm-hmm.
So it's a little bit strange in your notion of quantum duality. Like, what does this, in what sense has this anything to do with duality?
Well, that's the thing. So here we have this property, AJ times AI times AJ is equal to, AJ times this relationship here is equal to AJ. So that's kind of a local duality involving 3 vectors. AI AJ times AI AJ, AJ AI AJ is equal to AJ. That's the kind of a triple relationship that what I'm calling quantum duality property. So you sandwich it in and take any three of the basis elements. This only works for null vectors. AJ, AI, AJ is equal to AJ. That's quantum duality, as opposed to duality involving only two vectors. You get into the dual algebra, separate algebra, and then you define the Grossman structure on the. You can define a Grossman algebra, a Clifford algebra on the dual space, or you can define a Grossman algebra on the vector space itself, and then you can mix them all together, and you can define. It's just a different way of looking at things, I think. But so I like the idea that it's really a relationship, a local relationship involving three vectors. And that's what I'm trying to emphasize. My new insight just from today's session, that our seminar today, which I think is significant, actually.
I am trying to understand. First, we see in this table. No, the table is okay. Thanks. In this table, we see the Clifford product. I am okay.
Well, I'm not really even saying it's the Clifford product. I'm saying this product is due to this relationship. It follows from this relationship right here. AI, AJ, AJ, AI is equal to 1 when I is not equal to J. It follows directly from that relationship, no more. So actually this table follows from 3 directly, nothing more. Relationship between 3 vectors, nothing more. Any 3 vectors of this null vector basis satisfies that property of this table. That's what's important. Any 3 vectors, not all. So I should limit that discussion to any 3 vectors rather than saying this should be proven for any basis that is consistent with the.
You say 3, any 3, but you only have 2 indices, I and J.
Well, but that's okay. You can put a K in there too, and this defines the relationship between any 4 elements as well, because it reduces to 3 elements then.
No, maybe I don't understand what you mean by any.
Well, again,
3.
we'll go back to this multiplication.
Don't go too far. This is very
okay. This table follows from the other one, of course. Okay, I'll go back here.
But this is just a very elementary question. Like when you say any 3, so I have, say X, Y, and Z. Okay, so I have X, Y, and well, any 3. Okay, so suppose AI is X and AJ is Y. Okay, well, then but what do you do with the third one? Like, what do you do? What you said any 3. I don't understand this notion of any 3 when you have only 2 indices.
Well, remember I'm saying that when I define this matrix, this product here, let me go back here. I say that the rules of the algebra are exactly the same as rules of the matrix algebra. So it's an associative algebra. That's right, unless I say something about the multiplication rules I want to define, then I'm in trouble, because addition, or notice when I modified this, algebraic quantities with the property that x squared is equal to 0, they are added together using the same rules for addition and multiplication by scalars as the real or complex numbers. The trivial nilpotent is denoted by 0. So I tried to modify that to indicate it's like matrices over the real numbers. The same rules of matrix multiplication over addition and multiplication by scalars. So that's all I'm taking from matrix algebra then. Okay, then I defined the Grossman algebra by this. And now I'm trying to fix this, as you pointed out the problem, by saying that any three null vectors are defined by this.
As soon as you say any 3, I expect to see I, J, and K.
Yeah, okay.
Yeah,
well, that's right. In this multiplication table, I'm taking AI, AJ, and AI. Okay, so that let AK equal to A. I'm only taking a special case of that. I can see the problem. And it's perfectly, you're right. But you can reduce this. Take AI, AJ times AK. We assume the associative law, so I can write it as AI times HA times AK. And now I can expand that as AI dot plus AI wedge, and then I get a scalar times AI plus AI times a bivector. Well, there are problems. I'm not trying to say it's completely, that I don't have any problems at all, but I'm trying to make sense of it, without,
I have a feeling that your earlier papers, the papers that started by saying we have two different Grassmann algebras, that those papers didn't have that problem. But here,
well, I think it's more important to fix the problem than it is to go back to that. I think I understand better now that this is, like I say, an alternative way of defining matrix multiplication rather than the standard column and it's just a different way of looking at things, which I think is important. Namely, elevating the importance of null vectors as opposed to just idempotence. Everyone says quantum mechanics is idempotence and nilpotence, but this actually defines.
But in the earlier papers, you had null vectors that form one Grassmann algebra, and you had another set of null vectors that formed a different Grassmann algebra, and then because there are two Grassmann algebras, the notion of duality seemed to enter in a fairly natural way.
I've left those papers on the internet. I haven't tried to ResearchGate because it really traces out my own way of thinking, which I thought, especially now in light of this paper.
But it's almost like the notion of duality is disappeared.
No, I don't mean, no, you take any two of them, the inner product is a scalar, and that's, so it's hidden in that. In fact, Hestenes and Doran and had a group, they have a paper where they're actually interesting. They call it a mother algebra. Those are the geometric algebras of what they call neutral signatures, G, N, N. So you have N vectors which have square plus one, N vectors which have square minus one, and you correspond that to a matrix algebra of signature, 2 to the 2n. It's a very easy matrix isomorphism with these so-called mother geometric algebras. But, and they emphasize the relationship between duality and by introducing the corresponding null vector basis. Well, introducing G and N, so you have N vectors with plus square and N vectors with minus square, and that's called the geometric algebra N comma N. And then they write down the isomorphism between that and the matrix algebra of 2 to the 2n dimensions geometric algebra. But that's, okay, there's nothing wrong with that. And that emphasizes, again, the relationship, how you can sneak in just by going to a higher dimensional geometric algebra of neutral signatures, N comma N to represent. But, I worked with those ideas. And, in fact, in my book, New Foundations, I try to develop it as separate A's and the B's. Well, that's the interesting thing. If you look at the Pauli algebra, that really becomes the Pauli algebra of two nilpotents, A1, A2 times A2 times A1 is equal to 1. And that becomes, the 2 and 3 case become the matrix algebras of the Pauli algebras and the Dirac algebras. So that you're right, pointing out that 3 vectors, that becomes isomorphic matrix algebras of 2 and 3 dimensions. When you go to 4 dimensions, that's when you go to 4 nilpotent. Then you have these problems that you're talking about, which arise. But as long as you restrict to 3 vectors, then that's a local property. As I'm trying to emphasize, it's a much more, so that's right. I would say quantum duality is a relationship between any 3 vectors, and it should be thought of as a new duality type relationship that's defined in the algebra itself, rather than introducing a separate dual algebra. And people do all kinds of things, and they mix the Clifford algebra of the dual vectors and Clifford algebra of the vectors, and they do all kinds of things with all this extra structure around. Well, then you have differential forms, you have all kinds of mathematics that's been, but usually it's all then reduced to matrix algebra, matrix representation theory, reduces it all to linear algebra of matrices, matrix representation. Well, matrices are definitely
I think we lost.
Perhaps we lost the connection.
Maybe.
I'm not sure.
I guess.
Oh, you're
Okay.
back.
Okay.
You were in. Something happened to your connection, I guess.
I'm using an internet by Wi-Fi, and sometimes but it's much better. I'm not using AT&T anymore. I'm using T-Mobile, and it's much better. But there's still glitches if you use totally Wi-Fi, which I have now. 5G supposedly.
Okay. Well, I think I've sort of run out of questions. I understand that you'll be moving to Mexico, at least temporarily, Dr. Sobchak. So
Yeah, we have a flight 7:15 in the morning on Thursday. We'll get to Puebla at 7 in the evening, 8 o'clock or something like that in Puebla.
are you, is this vacation or are you
Well,
still
it's kind of a
working?
vacation. Yeah, it's a vacation. We still have ties. We spent basically, I taught for many years, and well, I first came to Fesquotitlan, and then I spent quite a number of years at Universidad de las Americas, Puebla. Professor Jaime Keller originally invited me to Mexico back in 1990, I guess it was, if I'm not mistaken. And that's where I had the.
Maybe you arrived to Mexico in 91?
Yeah, that's correct. And then Bishop Ojevich came to Mexico, I think it was in 1993, if I'm not mistaken.
Yes.
So at that, yeah. So anyway, I have we have my wife and I. My wife is coming with me, and she has. We're going to be. She's going to be taking advantage of the medical treatment in Mexico. She has some medical problems that we have close doctor relationships with doctors in Mexico. The American medical system is pretty bad. Well, I'm not going to go into a discussion of that, but it's interesting that the president of Mexico says that by the end of his term, which comes up in 2024, the Mexican healthcare system is going to be better than the Canadian medical healthcare system and the Denmark healthcare system, which is fantastic, I think.
Well, from my point of view, it wouldn't be hard to be better than the Canadian at the moment.
Well,
it's
I
not
think
saying very much.
Americans are jealous of your system that you have in Canada.
Maybe they
I didn't realize
are.
that they also compared to the Denmark President Lopez Obrador compares it to the medical system in Denmark. I don't know what's wrong with that system there.
All of these systems seem really, really good at first, but then bureaucracy and government get in the way, and then everything, deteriorates after that. So,
Well, anyway, but I'm glad that President Lopez Obrador has not compared it to the American medical system.
Well, at the moment, it looks better to me than the Canadian. But in any case, the main question for asking is just, I'm thinking about scheduling our next meeting, and I'm wondering, what your schedule would be, if you are preoccupied with being in Mexico and doing other things.
Well, I hope to be doing some mathematics too, as far as that goes. Wanda has more problems, but anyway, we'll be spending some time down there, at least probably a month. We'll spend down there.
We could perhaps delay our meeting. This is summer.
We can have it still. I have access to a working computer down there, so we can schedule it as normal as you see fit.
Okay. Jesus, you didn't really have an opportunity yet today, at least to talk about the issues that you mentioned in category theory and algebras. Maybe it would be appropriate if we were to schedule our next meeting to start with that subject.
Yes. Okay. I can organize better these ideas that I wanted to present today. Then I can start.
That's fine.
Okay. So in 3 weeks' time, but actually we're returning to our Wednesday schedule.
Okay, that's perfect. So what is the date on that?
Let's see.
It was 19 July,
Okay. Is that right?
Yes, I think so. 5. Today is 16, so 5. Yes, 19 of July. Yes.
Okay, perfect.
Mm-hmm.
All right.
Okay. Thanks a lot. It was very interesting.
Well, I found it very interesting too. Namely, you clarified 2 and 3. It should be quantum duality relating locally three vectors rather than 2. And that's the difference between ordinary. Anyway.
Yeah, if you can
very interesting.
If you can express that concept in more detail, I think that would be great. So maybe you could give us an update in 3 weeks and see whether you can do that.
Well, just give me 15 minutes at the end of
Sure.
next meeting.
All right. So,
okay, that's great. I really happy to talk today. It's helped me a lot. Also, this relationship to Professor Kaufman's ideas, I think, is extremely strong and very interesting in itself too, which pushed me more in the direction of quantum computers as a natural language quantum computers.
About the book of Osiewicz book is now in printed process yet.
Oh, that's exciting too, and I'm looking forward to seeing that.
And it is announced in the World Scientist page that it is for August. For August, you can dispose of this. The information is in the page of world scientists now, and you can maybe I can I don't know, but I'm going to take the chat from the where excuse me.
I'd like to see those other ideas that we've always talked about, this paper on the 3 reference frames. We never really did sort that out either, actually.
You mean return to something more?
Well, yeah, those ideas of Zbyszek Ojevich regarding, 3, that one thing I never quite completely understood. He's criticizing it's not really, Lorentz transformations really are not associative or criticism
Yes.
along those lines.
Mhm. Yes, we could definitely return to that subject. I think it's something quite different than we've been talking about for the last few months. But yes, let's keep that in mind. If that's something that you would like to return to, we could talk about relativity for a while. That would be. Yes,
think
were you were looking for a link to
This
that?
is very important, this fundamental, each observer splits his polyalgebra in a different way.
Now I have the link, then I can take and send to you.
Okay.
Sorry. Okay, you have now in the chat.
Yes, I see that. Yeah, so. Oh yes, I see. Yeah, forthcoming.
Coming in August. Then the process of edition has finished. It has finished.
It's perfect. Dr. Sotek, were you able to see that link that Jesus sent?
Oh, no, I didn't see it. Was it on share screen? I didn't see. Oh,
It
maybe
should be in a chat window.
in what kind of window?
Chat.
Ah, chat. Okay, yeah, I guess I have it then. Okay, yeah, I've got that. Yeah, let me.
So if you click on that,
Yeah, I can get to it then.
that.
Okay, I've done that, so I'll have it then. I can put it stuck. I can save it then.
Yeah.
Okay, I have it.
Great. All right then. Let's say goodbye for now, and I'll see you in 3 weeks on Wednesday.
Okay, thanks.
Perfect. I've enjoyed it.
Have a good trip.
Well, thank you.
Good day.
Bye for now.
Okay, goodbye.